Electrical safety. In this lesson, we're talking about why we should know about electrical safety, what can happen, electrical boxes and circuit breakers, fuses, grounding and static discharge, wall outlets, GFCIs, what call before you dig means, dangling electrical lines, and safety. Why should we know about electrical safety? The available electrical current in regular business and homes has enough power to cause death by electrocution. Many people work with electricity at work and in their own homes without knowing the dangers, and those dangers, like I said, can be significant. Here's some shocking stats. There are 30,000 non-fatal shock accidents each year that occur at the home. 325 electrocutions happen each year. The number of children that are treated each year due to wall outlet shock accidents is 2,555. 70% of child-related accidents occur at home under adult supervision. There are 60 electrocutions each year associated with consumer appliances. Electrical hazards cause more than 300 deaths and 4,000 injuries each year among U.S. workforce. And the sixth most common cause of workplace death is electrocution in America. What can happen? When electrical current travels through our bodies, it can interfere with the normal electrical signals between the brain and our muscles. So, for example, that can cause our heart to stop beating. It can cause our breathing to stop, our muscles to spasm. Pretty much everything in our body is controlled by electrical impulses sent from the brain or spinal cord to our body. And if these electrical signals are disrupted, it can be very dangerous. Electrocution can also cause fourth-degree burns, charring the skin, like you see here in this picture down here. You can get burned if electricity arcs or heats up nearby objects. So you don't just need to stick a fork into the outlet to get shocked. You can get shocked other ways too. Shock burns can burn internal tissues while leaving the outside skin with only mild injuries. So you can be electrically burned on the inside without showing the effects on the outside. What does this mean? Well, it means that if you do get shocked, if there is some kind of accident at home, you should go to see a doctor. An arc flash can also cause damage to eyes as ultraviolet and infrared light is emitted. Electrical fires can occur when cords or appliances catch fire. Some electrical fires happen because problems in the home wiring or appliance failure. However, many occur simply due to mistakes that homeowners make, like overloading electrical circuits or using extension cords inappropriately. So things like plugging too many cords into power bars, or plugging extension cords into power bars, or plugging power bars into other power bars, etc. The heavier the load we put on a circuit, the bigger the chances of danger. So what I'd like you to do is pause the video and watch number 2 and number 3. It's going to show you what an arc flash is and the danger associated with it. Electrical boxes and circuit breakers. All buildings have distribution panels made up of circuit breakers or fuses to control the flow of electricity. Each circuit in your house runs through the circuit breaker. If too much electricity is flowing, then the system shuts down to prevent damage or possibly a fire. They shut off or trip if too much electricity is flowing. They can easily be reset if tripped by flipping them like a switch. So these are the switches. So for instance, this might be the stove and the microwave. So if you have them both going at the same time, this might overload the circuit and it'll cause the switch to flip that way. If it does, the power in that area goes out. You need to go down to your basement and flip the switch back on. However, before you turn the circuit back on, you should turn off any devices that had caused a trip in the first place. If it starts tripping too often, you should call an electrician to possibly rewire your system. Fuses are like circuit breakers and are typically used in older homes or cottages and some vehicles. And they're these screw-in guys right there. If too much current is running through them, the component inside melts, immediately shutting them down and stopping the flow of electricity. So if that's the fuse, we're going to have a wire going in, a small wire inside, and then the wire coming out. This thin wire on the inside can't carry as much current as the wire on the outside. So if too much current is flowing through, this wire here will melt and it will stop the circuit. Now since the wire inside the fuse melts, once the wire melts, we need to replace the fuse because it's no good anymore. Grounding and static discharge. Electrical grounding is a means of moving excess electrons into the ground and away from you. Excess electrons can sometimes build up on electrical boxes and on machines and can be dangerous. To prevent electrical hazards, make sure the equipment is properly grounded. So how do we do that? Well, in the home, it's already built in. The third plug on typical outlet, so that guy right there and that guy right there, that's the grounding plug. They take excess electrical buildup and send it directly into the ground. Grounding works because the earth, the ground, has so many electrons that no matter how many are added or taken away, it's still essentially a neutral object. All the grounding wires in the home come together in the distribution panel, so you can't see it on these diagrams, but there will be a section where all the grounding wires come in, and it's probably just below down here. But you'll see all of the third plug wires, all the bare copper wires, they're all going to come together in the distribution panel, and then they're going to come together on the outside of the house, typically going into a water pipe that goes into the ground. This allows any extra electrons that are flowing around our plugs or in our home to be sent away from places where it could be dangerous. So our wall outlets, or our receptacles, are where we obtain our electricity for things like television, lamps, etc. And there are 3 main safety features of most wall outlets. Number 1, they're made of plastic. Plastic doesn't conduct electricity, so you won't get a buildup of electrons that can shock you on the outside of a typical wall outlet. We have polarized plugs. One slot is bigger. You'll notice this slot here is bigger than this slot. Therefore, the plug needs to go in the proper way. You can't plug things in the improper way because it won't fit. And third, most have a third round hole right here. And as we just talked about, that allows our excess electrons to be taken away through grounding. GFCI. So you might have noticed around your home, especially in places like the kitchen, bathroom, these specialized looking plugs, they look very similar, except we're going to have these 2 extra buttons on them. So let's see what those do. Now, a ground fault circuit interrupter, GFCI, is also sometimes called an RCD, a residual current device. A GFCI monitors the amount of current flowing within the outlet. If the current is being disrupted, like if you're being electrocuted, it will shut off power in 1/30th of a second. The GFCI compares the current leaving the outlet with the current coming back in. In a proper circuit, the current out should equal the current in. So if the current comes out of this plug here, and let's just say it's 1 amp, it goes into the device used, and with the current that goes back into the circuit, current is like the number of electrons. So the number of electrons going back in should be exactly the same, 1 amp. And this GFCI is going to measure, and we're going to see, okay, 1 out, 1 in. So that's good. Now, if something happens, like you're being electrocuted, then the amount in is going to be different. Let's say 0.5 amps to make our math easy. So since it's not the same, it shuts down the power immediately. If electrical current is lost, That's a maximum of 6 milliamps, so not the half amp that we were talking about in the last example. The GFCI trips. This turns the electricity off before severe injuries or electrocution can occur. Once a GFCI has been tripped, it must be reset by pushing the reset button, which is the red guy at the top. And this is similar to the circuit breaker that needs to be flipped after being tripped. Remember, you have to flip the switch. Well, GFCI, you need to push the red button. So if a GFCI you're trying to use doesn't work, check to make sure it hasn't already been tripped. You can push the red button to reset it. So a good example of when this would happen is if you're using an appliance in your water supply. Let's say you're drying your hair while taking a bath. If the water supply comes in contact with the current, either because the appliance falls into the water or there's a break in the cord, etc., electricity will flow into the water and possibly electrocute you. So we're going to have our wire coming in, and we're going to use our same example of 1 amp. Now, if the hairdryer falls into the water, what's going to happen is that some of the electrons are going to escape into the water. And the result is that the current coming out of the hairdryer is going to be less than 1 amp. So again, we'll use 0.5 amps. So since we have less coming back in compared to what left the wall outlet initially, it's going to shut down the circuit immediately and stop the electrons from flowing into the water, electrocuting you. Now, this can still result in a painful but non-fatal shock during the time it takes for the GFCI to cut off the electricity. GFCI wall outlets should be installed anywhere there's water present. This includes things like bathrooms, kitchens, outside. So if you have a wall outlet on the outside of your house, that should be GFCI as well. The GFCI circuit breaker can also be installed on some circuit breaker electrical panels to protect the entire branch circuit. So in case there's an overload in the circuit itself, you can shut off that using a GFCI specialized for a circuit breaker. So one thing to keep in mind is that one GFCI can be wired in series to multiple rooms. So you may have a bathroom without one, but if the circuit is interrupted, the GFCI will still trip in the other room and power will be cut to where you are. So if you have a multi-story house, and let's say you have a bathroom up here, call it bathroom, and you have a bathroom down here, and you have a GFCI here, and a we'll call it non-GFCI up here. If you trip the circuit up here, what's going to happen is that this non-GFCI is still going to be wired to the bottom GFCI. And since this reading is done so precisely and so quickly, even if you trip up here, it's still going to cut the power to this GFCI and thus this non-GFCI almost immediately. Call before you dig. Electrical lines, gas pipes, and other telecommunication services are often buried under the ground. Digging in the wrong spot could cut off essential services, not just to one home, but to an entire community. It can also be very dangerous because it can shock you if you're cutting through an electrical line. Damaged gas and hydrant lines create a safety hazard to you and others. In many locations, it's the law to call before you dig. So if you are digging anything substantial, anything below a foot below the ground, you should call to make sure you're not digging in a dangerous spot. Dangling electrical lines. Electrical lines can be damaged by storms or accidents. If you see a downed electrical line, stay at least 10 meters away from it. If the electrical line lands on your car, like say you run into a telephone pole and the electrical line is dangling on your car, you need to stay in your car and then call 911. If you get out, then you could be in danger. If you're in your car, you're going to be protected. A few more safety tips. Whenever you're working on electricity, make sure the power is off of the breaker. If you're not 100% sure you've turned off the correct breaker, turn them all off using the master switch. Now, this is both relatively easy and complex. If you're working on, say, a simple wall outlet, and you go down to the breaker box and you turn off the switch and then that wall outlet doesn't work anymore, well, then you've probably turned off electricity to it. But if that wall outlet wasn't working because of some other electrical issue, turning off the wrong breaker will still result in that wall outlet not working. In which case, if you turned off all of the electricity to the whole house, then you would have made sure that no electricity was going through that wall outlet. You should always inspect portable cord and plug connected equipment, extension cords, power bars, and electrical fittings for damage or wear before each use. Be aware that unusual warm or hot outlets may be a sign unsafe wiring conditions exist. Unplug any cords or extension cords to these outlets immediately. Ensure GFCIs are installed in wet or damp areas as the risk of electric shock is greater there. Do not touch a person or electrical apparatus in the event of an electrical accident. Always disconnect the power source first. Watch out for nearby hazards, power lines, water, or metal objects around the victim that may be carrying current, and do not plug in high amperage equipment such as space heaters, portable air conditioners, and other power equipment into extension cords. They should be plugged directly into working receptacles only. And the last main tip, guys, is that if you do not know what you're doing 100%, or if you feel the project might be too complex, call an electrician. They know what they're doing, and they're going to make sure that things are done properly. Rewiring your house incorrectly might not be damaging to you, but the person that moves into that house after you left can be left with a situation that is at best not ideal and at worst dangerous. And that concludes our lesson on electrical safety.